Breakthrough artificial intelligence from Nvidia and Stanford achieves groundbreaking results towards creating genuinely intelligent robots. Similar to OpenAI's GPT-3 or ChatGPT, a general-purpose robot agent should possess an easy-to-use and expressive interface for human users to communicate their intent. Now, a group of researchers, including those from Nvidia and Stanford, have presented a new multimodal prompting formulation that transforms various robot manipulation tasks into a uniform sequence modeling issue. It's called VIMA, or Visual-Motor Attention, which is a straightforward transformer-based AI agent that can perform tasks such as visual goal, one-shot video imitation, and novel concept grounding using a single artificial intelligence model. Multimodal artificial intelligence is a recent approach in which multiple data types, such as image, text, speech, or numerical data, are blended with various intelligence processing algorithms to achieve improved performance. Impressively, multimodal artificial intelligence often surpasses single-modal AI in many real-world applications. For instance, when applied to robotics, VIMA can not only handle multimodal prompts, but it also achieves superior performance while using just 1/10 of the training data normally required compared to other models. The use of prompts in training has become a crucial aspect of large language models like GPT-3 from OpenAI, which are trained with vast amounts of data and can be directed to perform different tasks. Techniques such as chain-of-thought prompting or algorithmic prompting demonstrate the significant effect that prompts can have on a model's performance in various tasks. In recent years, AI researchers have been utilizing large language models like PaLM with robotics. For example, Google used PaLM to directly control a robot with PaLM Saycan, which is an advancement of the Inner Monologues for Robots project. Additionally, Google showcased the ability to control robots in real time using a language model, and they recently presented their own Robotics Transformer 1 AI, which was a robot model that was also trained multimodally. But a group of AI researchers from Nvidia, Stanford, Macalester College, Caltech, Tsinghua, and UT Austin have showcased this new multimodal artificial intelligence model called Visual-Motor Attention, which has the ability to process multimodal prompts and thus surpasses even Google's Robotics Transformer 1. This means that with VIMA, an instruction such as rearrange objects to match this scene can be processed directly along with an image that illustrates the desired arrangement. The artificial intelligence model then utilizes the robotic arm in a simulated environment to perform the instruction. What's extremely impressive is that the artificial intelligence researchers trained the transformer model using VimaBench, a simulation benchmark designed by them, which comprises thousands of procedurally generated tabletop tasks in 17 categories with corresponding multimodal prompts and more than 600,000 expert trajectories for imitation learning. Shockingly, VIMA demonstrates superior performance even to models like Google's Gato, Flamingo, and Decision Transformer, with up to 2.9 times better performance across all model sizes and degrees of generalization. The largest VIMA model has 200 million parameters and requires considerably less data for imitation training, but can still achieve similar or superior performance compared to other methods. The AI researchers believe that VIMA lays a crucial foundation for future work, and even Google has agreed by stating in its own paper that VIMA's multimodal prompting is a promising future direction for its own robot Transformer 1, indicating that the use of multimodal models in robotics will continue to gain traction moving forward. What's even more impressive is that beyond multimodal artificial intelligence for robotics, researchers have also just introduced an incredible framework referred to as Masked Generative Video Transformer, abbreviated as MAGVIT, which can perform 10 different generation tasks, including frame interpolation, central outpainting, vertical outpainting, horizontal outpainting, plus dynamic outpainting, as well as central inpainting and dynamic inpainting, and even class conditional generation and class conditional frame prediction. Overall, the proposed framework aims to train a transformer-based model to restore a corrupted image. The corruption is modeled as masked tokens, which represent parts of the input frame. Specifically, MAGVIT treats a video as a sequence of visual tokens in the latent space and uses BERT, bidirectional encoder representations from transformers, which is a transformer-based machine learning approach originally developed for natural language processing to predict the masked tokens. The MAGVIT framework works by using two main modules. First, 3D vector quantized encoders produce vector embeddings, known as tokens, by quantizing and flattening the video into a sequence of discrete tokens. 2D and 3D convolutional layers are utilized along with 2D and 3D upsampling or downsampling layers to handle spatial and temporal dependencies effectively. The encoder performs downsampling, while the decoder, whose purpose is to reconstruct the image represented by the vector token supplied by the encoder, performs upsampling. Second, the MagVit framework uses a mass token modeling approach for multitask video generation. Unlike traditional mass token modeling in image or video synthesis, the proposed framework utilizes an embedding method to model a video condition using a multivariate mask. The multivariate masking approach enables learning for video generation tasks with various conditions, such as a spatial region for in-painting or out-painting, or a few frames for frame prediction and interpolation. The final video is generated based on the masked conditioning token, which is refined at each step after prediction. According to the experiments reported by the authors, the proposed architecture achieves the best published Freichett video distance on 3 video generation benchmarks. In addition, their results show that MagVit outperforms current methods in inference time by 2 orders of magnitude compared to diffusion models and 60x compared to autoregressive models. In addition to video generation, there's a new breakthrough artificial intelligence by Google that has paved the way for using extremely simple sketches to output incredibly impressive images. Text-to-image models have brought about a significant advancement in the field of machine learning, showcasing the capability to generate high-quality images from a given text prompt. However, these powerful pre-trained models still lack control handles that can direct the spatial properties of the synthesized images. In this work, researchers from Google Brain and the University of Tel Aviv introduce a universal approach to guide a pre-trained text-to-image diffusion model with a spatial map from another domain like Sketch during inference time. What stands out is that unlike previous works, their method does not require the training of a dedicated model or a specialized encoder for the task. Their key idea is to train a latent guidance predictor, known as an LGP, which is a small, per-pixel, multi-layer perceptron which maps out latent features of noisy images to spatial maps, where the deep features are extracted from the core, denoising diffusion probabilistic model network. The latent guidance predictor is trained only on a few thousand images and constitutes a differential guiding map predictor, over which the loss is computed and propagated back to push the intermediate images to agree with the spatial map. The per-pixel training offers flexibility and locality, which allows the technique to perform well on out-of-domain sketches, including freehand style drawings. Google Brain took a particular focus on the sketch-to-image translation task, revealing a robust and expressive way to generate images that follow the guidance of a sketch of arbitrary style or domain.